as a whole and try to understand it, describe it, the formation, the evolution, and why it looks the way it looks. So in this sense, it's about space. Space is much more than what's a little bit beyond the atmosphere of our Earth, but there's a lot there beyond the atmosphere of our Earth. So what I'm going to talk about is observing the light of the distant universe, because it's from the light that we observe, we can know about what's out there. And one of the leitmotif of this presentation, as you would see, is this deep connection that there is between the infinitely big and the infinitely small. So by looking far away and looking at very large scale, we are trying to understand physics, but we are trying to understand the same type of physics that govern the infinitely small, that is the structure of space-time and even fundamental physics, which usually here on Earth get tested by building big accelerator to go at the subatomic level. In the universe, we can observe, not build, but observe signature from physical processes that reach energies that are much higher than any kind of energy that we could reach here on Earth. But the same physics need to describe both. So this is the interesting thing. And why do we do that? Well, because we are born to explore and we are driven by curiosity. That's what drives us to do all this. These are my twins when they were small. And as you can see, as we are born, we are really young, we already explore, and we explore in several different ways. We can explore doing experiment like in the lab, or we can explore going around and trying to actually find things and touch things and see them firsthand. And this continues, and as continues in the whole history of humankind. Exploration at the time of Columbus was, to go on a boat and find new world. And then with the space age has been actually going into space. There are rockets that are both manned and unmanned mission, both for this type of exploration, but there are also telescopes built on Earth that peer far into the sky, and that also it's a form of exploration. And as a cosmology, you mix all this together, because since you are looking at the universe at such a large scale, we'll never be able to actually go there, but this sort of remote observing that still allows us to explore and understand. Now there is, so the key concept here is that the universe is comprehensible. And the physics and chemistry and mathematics, as we know them, we learn them at school, or we test them on Earth or in a lab, describe and apply to the entire universe. And now, if you want to go in the philosophical direction, there's a lot of philosophy to be discussed here, why human can understand the entire universe and maybe all the other animals on Earth can't, why a dog can't, why you wouldn't build an observatory for the dog or something like that, right? So in this sense, it's a tall order. And how is not necessarily why. And so as in all development of all sciences, you start from the how, and then you try to get to a why, but the why, it's a different kind of question from the how. And it's easier from the scientific point of view to describe the how, and the why you may get you into metaphysics and along that direction. So why do I think that one can even understand the entire universe, while it's difficult enough to understand the model things on Earth, which are much smaller scale and much closer to us, which we can touch and we can make experiment. While in the universe, we can't make experiment, we can only do observations. We sell to the funding agency that we make experiment and we are scientists in that way, but we can only make observation in reality. And so it turns out that this is based on a very simple observation. That is, electromagnetic forces or things like that are very, very strong, much, much stronger than gravity, but they are both attractive and repulsive. And so as you go to larger and larger scales, they become less and less important. And gravity that is so weak at the end is the one that wins as you go to very, very large scales, because gravity is always attractive, with some specification that we will understand later on. But gravity, as we understand it, is attractive. And that's why it's simpler, paradoxically, to try to understand the whole universe than to understand what's going on here on Earth. All right, so this is not new. It's not new to try to learn about physics by looking up the sky. The first one who did that was Galileo Galilei. Galileo contributed to the beginning of the scientific revolution and gave us modern science. And again, this leitmotif of connecting the infinitely big with the infinitely small. So when I say infinitely big and infinitely small, let's talk about scales. If the solar system is a coin, and we know how long it took us to send even a probe to the edge of the solar system. Think about how long the Voyagers has been traveling to actually get there. Now, the nearest star, typically, it's kilometers away. So from where I'm sitting, it will be at the Arc de Triomphe. And then on those scales, if you want to think about the size of the galaxy will be the size of a continent. And so we are talking about extremely large scales. So there are as many stars in a galaxy as grain of sand in a cubic meter of sand. And galaxies for cosmologists are little more than points. And there are as many galaxies in the universe as grain of sand on the surface of a typical beach. And there are more stars in the universe than grains of sand in the entire Earth. So that should give you a flavor of what scales we are talking about. And this is, again, sort of to bring us back to what the scale is we are talking about. Now, cosmology has now a standard model, and this has been the case for at least the last decade. And this model has few numbers, and these few numbers describe quite well observation of the universe and give us a pretty good picture from shortly after the formation of the universe until today, but on the very large scales. And about this time last year, the Nobel Prize was given to this person, I don't know if you remember, Jim Peeble, for contribution to our understanding of the evolution of the universe and discoveries in physical cosmology. This is the person that gave us the cosmological model. When he thought it up, it was not yet the standard cosmological model, but it became the standard cosmological model and was suitably recognized because of this. So at the base of this model, there is what 99.9% of cosmologists would agree, is the fact that there is a lot of dark matter out there. So not everything that shines and that we see, it's what's out there. And we somewhat know that because we know that in our solar system, the sun shines, but the Earth doesn't. It reflects, but doesn't shine. And I don't shine, my table doesn't shine, and so on and so forth. But we are talking a little bit more than that. And so the idea that there was dark matter in the universe, and let me see if I can show you. This image usually people remember. It's due to the beginning of the century, to the 20s, when astronomers started looking at the motion of galaxies in clusters of galaxies and realized that they were moving too far to justify that these objects were gravitationally bound. And so there must have been a lot more stuff than what lights up. And that's the name of dark matter, how the name of dark matter appears. And then, of course, once we put that in the context of a theory of gravity, as Einstein explained to us now, space tells matter how to move, and matter tells space how to be modified, then gravity is reinterpreted as a modification of bending of the space-time, like, you know, putting some heavy weight on a mattress. Then this it's sort of easier to try to find the signature, observational signature of unseen matter. And we've seen in spectacular images like this one taken from the Hubble Space Telescope, where this, let's see if you see this, my cursor, these images here that looks like rings around a big bright objects are distorted images of background galaxies, which light has been bent so much that there are multiple images of the same objects, but light doesn't travel on what we think a straight line anymore, because there's a lot of stuff there that has been bent in space-time. And the justification for all that stuff cannot be found in what lights up. So there's a lot of dark matter out there. And in the standard cosmological model, this is the cosmic pie. These are the components of the universe. 25% is dark matter. Atomic matter, like me and you and everything else we've touched and we've interacted with, it's only 5%. And there's a heck of a lot of something else that nobody's really sure what it is. And that's the story I would like to tell you of more or less how the community got there. So this model had a spectacular success. It's one model, 6 parameters, which are 6 numbers, based on mostly on physics we know, which understand and describe 13.7 billion years of evolution of basically everything. So let's take a step back and go a little bit easy and start with another fundamental concept, that measuring distances, especially at cosmological scales, is difficult, but measuring velocity and especially recession velocities, it's easy. So we have been taught in school that light is a wave, and a little bit like sound waves, when something comes close to us and emits a sound, we hear a higher pitch. And when something goes far away from us and it's moving going far away from us and emits a sound, we hear a lower pitch. And this is due to the fact that it's emitting a wave, and the wavelengths get compressed as this comes towards us and stretched as it goes away from us. So for the light is the same. Now, the wavelengths of light is relatively easy to measure because it looks like color, or you can take a spectrum. And that's why measuring velocities, especially recession velocities, or velocity along the line of sight, is easy. Measuring distances is very difficult, but this person got a telescope, a space telescope named after himself. So it did 2 or 3 very important things. And one of those, it's making a connection between these two quantities. So he looked at a whole series of galaxies. This was again at the beginning of the 1900s. And he realized that most of the galaxies that he was observing were receding from us. And then he realized there was a linear relation between distance, which he could measure some other way because these objects were nearby enough, and therefore he could measure approximately distances, with the recession velocity. And so there's that little constant of proportionality called H, is called H after Edwin Hubble, after Hubble. And now this, it's a relation between something one can observe, that is the wavelength shift of an object, of the spectrum of an object, the color of an object, its recession velocity, and its distance. Now we can measure distances. And not only that, but by looking around as this object, it says they are always going away from us. I can't believe that we live in a special place in the universe and therefore everything is running away from us. I have to believe in the Copernican principle that I'm not a special observer, and therefore any other observer would have to observe the same. And the only explanation for this is that the actual universe is expanding. It's not that objects are running away from me, full stop. So yeah, that's another of the very important thing that he found out. So today we know that the universe, there are galaxies distributed all around the universe. And if I can show you here, this is a fly-through animation from a real survey of what the distribution of the galaxies in the relatively local universe look like if you were able to fly through them. Now, of course, you can't fly through them because to do that, you would have to travel much, much, much faster than the speed of light, and you can't. But you can build that into a computer using actual real images taken by a telescope. So there are a lot of galaxies out there, and they are not uniformly distributed. They are distributed in what is called the largest scale structure of the universe. All right. So let me introduce another fundamental concept, which is looking far away in space. It's equivalent to looking back in time. And this is because light travels at a finite speed. That's again due to our friend Einstein there. So when we see the light from the sun, that light was emitted 8 minutes ago, but the sun is not that far away. It's still in our solar system. So when in our galaxy, we look at our galactic center, say that we are here and we look at a galactic center, which is unfortunately in the southern hemisphere, so we can't see it from here. But we look back in time about 28,000 years. When we look at the Andromeda galaxies, we see it as it was about 2 million years ago, and so on and so forth. So when big telescopes, and this is a big telescope from 20 years ago, now we can do even better than that, look at galaxies far away, they can see galaxies. So if we are sitting here, we are looking out at the telescope can only see a cone out, and sometimes can only see a slice of the cone because, we want to avoid the galaxy and things like that. Each of these little points here that you can't resolve, it's a galaxy. Down here, which was the edge of this survey, this was the 2-degree field galaxy redshift survey, was 1.1 gigayear from the Big Bang, and this is, 11 gigayear from the Big Bang, and this is 14 gigayear from the Big Bang. But we're doing cosmic archaeology, but we do not see bones like an archaeologist will do digging down on Earth. We see the past, life and kicking. So we are here, we look back, and how far back can we actually look? Well, if the universe is expanding and everything is flying away from us, imagine we run the movie backward. If we run the movie backward, when you have something contracting, what usually happens? That something warms up, gets denser and warms up. So in the past, the universe must have been hot and must have been dense. It comes to a point where if it's hot and dense enough, it must have emitting radiation. And actually, we have seen that radiation, and that's a wonderful story. So if we now try to describe this in terms of physics, let's put it this way. The universe today, it's colder, and therefore us form atoms. Most of what is out there in the universe is hydrogen, so the hydrogen is neutral. It's therefore transparent, and photons can travel through it. We can see things. But as the universe in the past and far away becomes hotter and hotter, at some point it's hot enough that the atoms are ionized. If they're ionized, then there are electrons bouncing around, and the photons will interact with those free electrons, and at that point the universe becomes opaque. It's a little bit like looking up at the sky on a cloudy day. and you look at the surface of the cloud, the photons from the sun bounce in the cloud, and so you can't see the sun through the cloud. But when they arrive at the surface of the cloud and then they travel undisturbed to you, and you look up, you see the surface of the cloud. So the same thing happened with that, and that point between the universe hot and ionized and the universe becoming neutral, then it's called the last scattering surface. So here's the story, how it goes. So if the universe was expanding, if it was expanding and it was cooling, it must have been hot and dense in the past. Now, Fred Hoyle, which is another of this giant of the development of physics and cosmology, said, do you think the universe was born in a big bang because it was hot and dense, like an explosion? And he said it as a joke, but then the name stuck because it was the proposer actually of a steady state universe. But anyway, it turns out that if the universe was really born out of a big bang and a hot state, then that radiation should be somewhere and somebody should be able to see it. And many people in physics department were actually trying to do that experiment. It turns out that two radio engineers working at Bell Lab realized that there was some sort of spurious signal in their antenna, here they are, and they couldn't get that out. They tried to check their instrument, they tried to check their antenna, there was this emission, and they concluded it's not in the instrument, it's in the sky, and it's uniform across the sky. And it turns out, Nobel Prize in 1978, that was indeed the echo of the Big Bang, this hot radiation left over when the universe was in this hot and dense state. So this is called the cosmic microwave background. In the paper from that epoch, it's called the echo of the Big Bang, the primordial fireball, the cosmic microwave background. And we know that it comes from the universe was about 380,000 years old, and today is 13.7 billion years old. So it's really like seeing the baby universe. So a quick history. In the 60s, Penzias and Wilson saw this uniform radiation, but of course we know that today the universe is not uniform, so it must have had some initial seeds for structure and for galaxies. But there was a big race to try to see those seeds, and those seeds were difficult to see. At the end, in 1992, a satellite it was in orbit around the Earth, it was a polar orbit, saw them for the first time, and it was recognized, the team was recognized the Nobel Prize in 2006 for actually seeing this fluctuation. And that was another indication of the presence of dark matter. Because if there is not matter that help galaxies to form and create the scaffolding for galaxies to form, we should have seen much bigger fluctuation in that primordial fireball, which we haven't seen. And the fact that it took so long to see them, it's a clear indication that there must be a scaffolding that helps structure to form. Now, of course, once you've seen the baby universe and you've seen the signature of this primordial fireball, then you want to know more about that. And then a lot of other experiments followed. Some of them were ground-based, some of them were balloon-based. And then finally in 2000, and one was WMAP was launched, and then in 2003 the results were reported, and this is the map that is shown. So I hope it's clear to everybody that the universe is not an egg. This is a way to represent the celestial sphere on the plane, like sometimes you do with actual maps of the Earth. And what you are seeing, this red band here, is the emission of our own galaxies, because once you see the entire sky, there is also the radio emission of our own galaxy. And of course, there could not be a talk to women in aerospace without a picture of a rocket going up. The WMAP experiment was up here. This has been launched from K. Canaveral 2001. And I'm showing this picture because I was in the science team for this mission. So I have this picture. I don't have the picture of the following experiments. But there has been a following space mission, which is the Planck mission, that made this map, which is very similar to the previous one, but at even higher resolution and a much, much better signal to noise. So what we are seeing here are small perturbations of this primordial fireball that are the rumbling of the Big Bang or the seeds of galaxies. So these are small hot and cold spots in this primordial radiation that correspond to small density perturbation. And it's the statistical properties of this perturbation that can give us very precise information about the properties of the universe, the composition especially, and how the different elements of the universe that compose the universe. Now, I want you to understand how exquisite these experiments are. So we are talking about minuscule effect. Those perturbations are 1 part in 100,000 or even more, depending on the scales you are looking at. So Planck satellite has basically the capability of measuring a temperature fluctuation, which is equivalent to measure the temperature of a bunny on the moon from Earth. So when we talk about precision instrument, that's what we are talking about. And this has been very useful because, as we say, if today, if we compare the evolution of the universe to the evolution of a human being, when we look at the cosmic microwave background, we are seeing an infant. We are really seeing a baby within a few hours from being born. And then as we see the universe farther away and then closer by and then closer by, is like seeing like a picture book of the life of this person. So there is a lot you can learn about this person if you can have a scrapbook or a picture book of the entire life from the beginning until the person is mature. Now, this is to understand intuitively what that is, but to be a little bit more precise and quantitative. So we saw the seeds of galaxies in maps like this of the baby universe, and then we look at the large scale distribution of galaxies or the evolution of 13.7 billion years. And with the galaxy survey, we've seen and we trace this on very large scales, but how do we actually do that? Now, I don't want to go through the equation, but I want to explain to you what this equation means and what one can read out of the mathematics that describes all this. So I like to explain it in this way. It's a little bit like waking up in the morning and looking at the surface of the sea and seeing tiny little waves, but noticing that there is some wind. And the wind keeps going the whole day. And as the winds keep going, you know that the wave will grow in the sea, and they will keep growing and will keep growing until, by the evening, you can even surf on them. Now, by observing the waves and by measuring the properties of the wind, if the wind is gravity, and the waves are these perturbations that we see in the primordial universe and the large scale distribution of galaxies. So you could learn, for example, whether the sea is made of water or whether the sea is made of honey or whether the sea is made of jam, because you wouldn't form the same wave whether it was made of oil, jam, water, or honey. And you would know about the strengths of the wind, so you know about the strengths of gravity. And so basically the kind of equation that the cosmologists use to describe structure formation and learn about the composition and evolution of the universe are not too dissimilar from the equation that you would use to describe the wave under the wind. But let's stop there and not write them down. And so I want to introduce you to one of the efforts of the telescopes to actually going after this large scale distribution of galaxies. This is a survey that has finished a few years ago, but still has produced one of the largest maps of galaxies, of three-dimensional distribution of galaxies in the universe. So this is the picture of the telescope. This telescope is not among the biggest one. This is, 2.5 meters telescope, but it really, so you want a very, very, very big telescope to see very far away, but then the field of view is typically very small. If you want to survey a lot of the universe, and therefore you want to survey a lot of the sky area, you can't have a too big telescope, otherwise it will take you too long to actually cover the entire sky. So that's why there is still quite a lot of room for playing for mid-sized telescope. And this is actually a small fraction of all the data that the telescope took. And now each point is a galaxy, and the galaxy is a little bit color coded to show which one are the one more nearby and which one are the one that are farther away. But again, this is a small fraction of the data that is there. All right, so we know that there is dark matter. We had several evidences of dark matter, and we know that the dark matter is a little bit the scaffolding that allow these waves to grow, and there's more there than what actually lights up, which are the galaxies. And this is puzzling enough because in the standard model for particle physics, there is nothing that looks like the dark matter we need to explain the observation out there. But at least it's matter, and at least it's something that could be described by, say, a particle that, people that do underground accelerator experiment haven't seen yet, but maybe they have to try it harder. But there's still that option open. But let's go back to Hubble. Hubble, 1920s, says the universe is expanding. All right, let's let cosmologists be like Hubble, but do it bigger and better and farther away. What did I find in 1998? Holy cow, oh my, it's not just that the universe is expanding, but the expansion is actually accelerated. Now, these people got the Nobel Prize in 2011 for that. And let's try to understand why the Nobel Committee recognized this work. So if the universe is made of matter and gravity is the main force that is at play when you go to large enough scale, imagine that there is an initial kick like the Big Bang that set it all off to expand. What do we expect this expansion to do? Well, we expect this expansion to sort of slowly slow down, because gravity is an attractive force. But we would never have expected this expansion to actually start accelerating. And so when I was trying to teach this in my class, I used to have a teddy bear, and I used to throw the teddy bear in the air and say, if I throw this teddy bear in the air, do you expect the teddy bear to start going up and slow down, and then maybe eventually come down, unless it escape velocity, and at that point it keeps going up, but it will slow down going up? Or do you expect the teddy bear to say, oh, I have an engine on my tail, and now the rocket has switched on, and I'm going up and accelerating? You don't expect that. So similarly, we were not expecting that, or cosmology were not expecting that for the entire universe. And yet, the observations around that were released in 1998, but then continue being confirmed and reconfirmed and super reconfirmed, told us. So how did they do that? And I want to give you a flavor of how that went. So they did that by looking at supernovae. So what are supernovae? Supernovae are stellar explosions that, for a reason that we understand reasonably well, when a star reaches some critical mass because stuff is falling into it by a companion star, it can't take it anymore and explodes. Now, since this critical mass is pretty much the same for all the stars, then the luminosity of the explosion is pretty much the same for all the explosions. And the nice thing of this is that these explosions are very, very powerful and very, very luminous. So in a few days, a single star can be as luminous as the entire galaxy. Now that's a lot. The key is that the galaxy, it's on for a very long time, while a supernova is on only for a few days. And so it's difficult to see them because they are on only for a few days, but the moment you see supernova, then they are wonderful standard candles. And if you know how bright a light is, then you know how far away it is. You know how far away it is, you can measure the recession velocity because Hubble told us how to do that by looking at the spectra of this object, and you can make a map of distance versus recession velocity, and you can really find out whether the expansion of the universe is slowing down or accelerating. So here I want to ask you whether you have sharp eyes to see a supernova. These are two images of the same galaxy, the Whirlpool galaxy, before the supernova went off and at the supernova maximum. And you should be able to see it even by naked eyes. Oops. There it is. So this kind of explosion can be seen basically, halfway across the universe, which make them very powerful to trace the evolution of the universe. So here it is, the largest scale of the universe, and we've learned about the composition. So what makes the universe accelerate? Well, we don't know what it is. It's not matter, so we call it energy, and the genius name is, after dark matter is dark energy. It just makes the expansion of the universe accelerate. So here it is. Back to the cosmic pie, we and all chemistry are a small minority of the universe. A lot of it is dark matter, but there's a lot more which is dark energy. So we are left with a series of questions. Why is this function of the universe accelerated? It's simple to give it a name and say, let's call it dark energy, but what is it and what makes this function accelerate? There's nothing in our standard model of physics that can do that. Well, there's nothing actually. Einstein in his equation at some point put a term that may look like an accelerated expansion, except that they put that term because he didn't know about Edwin Hubble observation about the expanding universe, and Einstein wanted a static universe, and his equation of gravity told him that a static universe was very difficult to get, but he added this term and said, yeah, there you go, so I get a static universe. When Hubble published his result about the expanding universe, apparently Einstein went, do. But it was apparently was not wrong. Maybe there is that term that could be used by tweaking it a little bit to give you an accelerated expansion. Also, why was the primordial universe not homogeneous, right? Who and what put the seeds of the galaxies there? The one that we see in the cosmic microwave background, that's still open. What is the dark matter, of course, and are there any other players that we know are in the standard model, like for example neutrinos, that may be important player in the structure formation of the universe? So the universe is a lab, and we can do experiments like observations with it at a much higher energy than those that we can test here on Earth, and we can of course explore much bigger scales where new effect, like for example the dark energy or the accelerated expansion, shows up that will not show up in labs on Earth. And again, understanding the universe at the large scales, a deep fundamental link with basic fundamental physics. And so I leave you here with this, that understanding the universe is an effort of the entire community, but it's definitely not cheap. And a lot of it involve effort of building big machines and big telescope, many of them on Earth and many of them in space. Few of them in orbit. We know of the Hubble Space Telescope that is in orbit, but now, for example, cosmic background experiment that go in space end up being at the Lagrangian point because it's much more stable than an orbit where you start having day-night and thermal perturbations and things like that. And some are even thinking about building telescope on the dark side, which is not the dark, it's just the other side of the moon, to protect those telescope from radio emission and radio interference from Earth. And I think this is a good time to stop and open the floor for questions. Thank you.
Okay. Thanks, Licia. It has been really, really an interesting and understandable talk. Now it's question time. In the meantime, that with the aim of giving some time to you for writing questions on the chat, I will take the chance of asking to you a few questions. And Licia, during your presentation, you already talked about when you were a girl. You show some pictures. You have explained about you enjoy experimentation and discovering everything around you. But my question is, since you were a girl, you already knew what you would become, a cosmologist or just a scientist or engineer? Or
no. No. So I was curious, and that was the time where the standard model of particle physics was coming together. And so a lot of the documentaries that were on TV, remember there was no YouTube and no internet and not any of that, were about quarks and fundamental particles. And I thought that was really cool that we could understand the invisible just by thinking about it and applying some rigorous way of thinking and devising experiment. But it turns out that to do that, you need math. Because unfortunately, mathematics is the language of nature. And it turns out that I didn't like math that much. And it turns out that I wasn't particularly careful. And I was like, 1 + 1, could be 2, could be 3, who cares? Why are you asking me this? And so I ended up actually doing classical studies for a few years. And where, there's basically very little math. And then after doing that, I wasn't particularly satisfied because it seems to be a little bit wishy-washy, and then everybody could offer their own interpretation to whatever. And I thought that something a little bit more rigorous would, work better with my personality. So I switched field and I went to study physics rather than math, thinking that that would save me. But, I had to bite the bullet and learn math.
Okay, that's a great story. Thank you for sharing with us. Another question, is this, in this pandemic period, some people are complaining about the money waste in a space field, okay? They say that the missions, the scientific missions, it's a lot of money. But how you value the aerospace sector, both positive and negative sides, and the impact on our society?
Okay. So I think this is my personal point of view, and there are several aspects to this. So let me see if I can spell them out. There is the near and immediate danger, which is what's going on right now during the pandemic. And then, of course, you should devote the resources that you have to manage that. If it's needed, lock all of us at home, which is what happened last year in March, and develop a vaccine, study epidemiology, do that. That's the short term, because it's the immediate and grave danger. And there is a bigger question, which is you want to have science developing. You can't be stuck in the Middle Ages, and you're not stuck in the Middle Ages if you develop science, and you need to do that at the level of international collaboration, but also at the level of every single nation, and at every level, even at the level of getting people interested in science in school. And what I like to say is that the science, it's like a human body. If you hurt your little pinky, you can't think straight. So you can't take science and say, but I throw this bit of science away because I think it's not useful. My little pinky is not useful, so cut it away. Now, if your little, if your little pinky is really beyond repair, in some extreme cases, it may be cut away, but that's not the healthy way to go. And again, without science, there's no applied science. And so there you go. So studying the universe is not gonna directly cure the common cold, but you cannot have a technological society, which is what we want, if you don't develop science. And you can't cherry pick what you develop of science. Of course, you must have priorities.
Absolutely. Yeah. Change the subject. Yeah, it has been really interesting answer. I agree with you. But during your presentations, we have seen a lot of scientists involved in the current knowledge of the universe and their research. But I'm not sure, but I think that all of them are men. Do you think that your career will have been easier if you were a man, or you think that to be a woman has not any inconvenience on that?
All right. So first, we stand on the shoulder of giants, and society has changed a lot during the past 100 years, even during the past 20 years. So if you're trying to give a sort of historical development of a field, then you are looking back in time. So it's much more likely that the big personality you find tend to be men for a heck of a lot of reasons, right? Both societal, and both of who write the history is always the winner, right? So there are these two components. Today, the situation is a little bit different in the sense that there are many more women that start the scientific career, which doesn't mean that necessarily, the famous glass ceiling, right? They arrive at the position of power and being able to then write the history according to their interpretation, which is a different matter to solve. Whether it would have been easier for me, I don't know, because it's a parallel universe and not the universe I live in. So it's very difficult for me to say.
Okay. Thank you. And last but not least, do you want to transmit a message to the new generations?
Be curious.
Okay. This is exactly the same message that Ana Maria, that is one of our colleagues as a public, she just said, curiosity is the engine.
Yes. But that's the beginning. Be curious, but then you need a methodology, because we can be curious, but then without a structure to ask the right question and find the right ways and the right tools to go after this question, it's very easy to fall off the going in the metaphysical, or in everything is aliens, or who knows. So in that sense, one also needs some guidance on how to be curious. But first you have to be curious.
Okay, great. Okay, some questions that people asked. The first one is from Cinder. Sorry for my pronunciation. Sin Hari. Say, hi, as many explosions are happening in the universe, do you think that one day our Earth will also explode?
Very interesting question. Let me break it in two parts. One part that is the much less speculative, and one that is much more speculative. So, how many explosions are happening in the universe? I have the impression, and many other astrophysicists have the impression, that anything that can go bang in a universe will go bang. Okay. And so, for example, for supernovae, there's about 1 supernova per century per galaxy. Now, it's not a lot if you look only at one galaxy. If you figure out how many galaxies there are in the universe, if you remember the parallelism with the grain of sand, then there's a lot of those. So there are a lot of explosions going on. And not only supernova explodes, there are also novae who explode. There are also other type of explosion here and there. And there are, all this collision and explosion that give us gravitational wave, as we have seen, in the spectacular result from 2016 to today. So yes, about the explosion of the Earth. So the Earth, as far as we know, with the physics we know today, cannot explode. It's true that our sun will eventually end up as a red giant, and red giants grow a lot and swell up a lot. And when the sun will swell up, will probably encompass a lot of its planet around. However, if I want to be completely speculative, we don't know what dark energy is. Right? So there are some theories of a dark energy that says that if it is a particular type of energy of the vacuum, if you push this model to the limit, it may turn out, look how hypothetically this is, in the future, that this accelerated expansion will also overcome first gravitational attraction and even electromagnetic attraction. And then if that is the case, then everything will rip apart. That is called the big rip scenario. And then in that case, you may say that even the Earth will explode. But, by the time, it's very speculative. Don't go and bet your money on that just yet.
Okay. MSJ asks, will the launch of the James Webb Telescope represent a breakthrough in this field?
Yes, because you're having a completely new capability. So if we've seen what Hubble has done to the field of both astronomy, astrophysics, cosmology, so we can expect something very similar from what among friends is called JWST. The James Webb. Yes. Although I think the better discoveries are the ones that were not expected. So we'll see.
Okay. We'll do another speech in some years and to talk about the new information of that. Okay, Ana Maria she's saying she's agree with your answer about the curiosity. She said, right, hypotheses and demonstrations to be intuitive is another characteristic of a lot of scientific, including Einstein.
Yes,
Then there is another
There is creativity also in science, yes. But again, you can be intuitive, but based on knowing your physics and knowing your math and then proving it. You can't just be intuitive and leave it at that. Yeah.
Intuitivity and imagination are necessary for any kind of job. Okay, Esha asks, what do you think about number of dimensions exist in the universe?
Very good. So the spatial dimension that we see and we test, we know there are three, at least at the scales that we see and we test. Now, Einstein taught us that in reality, there's more than the three spatial dimensions, that the time can be seen as another dimension, and we shouldn't think about space, we should think about space-time. So now we are at 4. Now, people that try to connect, say, to go to the very small scales and try to understand the very fabric of the space-time and its interaction with fields and particles, etc., they tell you, look, in order to make, say, the quantum world agree with general relativity, I can't do it in any other way than postulating a theory that has many extra dimensions than the 4 that Einstein gave us and the 4 that we have tested at the macroscopic level. Even 11 dimensions. But we don't have any experiment that has actually seen these extra dimensions. So we know for sure that we are the 4 that Einstein gave us. And there are theory and speculations that add the extra dimension, and there are people that maybe dedicate their own career to actually study those theory and find out whether there could be experimental tests for those. But we haven't tested them in the lab just yet.
Okay, interesting. I didn't know. Really interesting. Florence is saying, thank you very much for the knowledge you shared. It was lovely to hear you. I would love to attend other conference. Best regards, Carmen.
Thank you.
Yeah, a lot of messages of thank you. Eva saying super interesting presentations. Huge thanks, Licia, and Woman in Aerospace. And no more questions for now. A lot of message to say thank you very much, and I say you again, thank you for your time, thank you for your effort. It's really nice, and we are really so proud to have people like you in our talks. We're also proud to announce you that next speech, it will be done for Gisela de Trey, that she's already with us today. She will talk about a way to live in Mars or in space. We are waiting for you next month in the next talk, next speech for inspiring women in the space field. Thank you very much, everybody, for your time and to be here with us.
Thank you.